Okay, it's 11:30, so I'm going to get started here. We're going to start with sort of a recap of what we know about the lasso, and you guys can tell me, since I wasn't here on Monday, what you have covered or not covered. And so the one little thing we had that I was even showing you last Wednesday is this little thing with different loss surfaces. And I think the first most important thing is before you do anything with lasso or ridge or anything like that, so let's turn off the ridge, we'll turn off the lasso, and let's turn off this line. What are the things we can say? The things we can say are that there is some true value that we're trying to get to, which is this little green dot here in the X and Y axis. On the plane, there's this little green dot of what we're really trying to get to, and there is a bowl above it. And that bowl represents the loss surface. So this was, I guess, the first fact in our little quest here that we observed is that, so in the example that we're doing, there is beta hat 1 and beta hat 2. So there are two dimensions that we're trying to estimate, two parameters. And there is some true value that we would like to get to. There is some true value, beta hat, let's call that beta 1, beta 2. And the loss we observe is some kind of bowl with a minimum near beta 1, beta 2. Is a bowl with a minimum near beta 1, beta 2. And we put these we plot this in 3D. We put beta 1 on the x-axis. We put beta 2 on the y-axis. And then we let z equal this loss, which is a function of beta hat 1, beta hat 2. So that's what's going on here. And that is this picture over here, this little bowl, this bowl-shaped thing. And that green dot represents the true value we want. That's the minimum of the bowl. And the bowl is... it has some height. That height is the irreducible error that you will never get rid of, just like we saw many, many weeks ago. It occurs to me, actually, you might notice this bowl doesn't look right. Why? How come I just said that the bowl is centered at the green dot, but then if you look at the picture, if you look carefully, let's see, can I make it bigger? Can I make it smaller? I can't change the size of this picture no matter what I do. Okay. Good to know. What do these buttons do? Whoa, that's cool. Okay. Let's go back to this one. What's going on here? Why is it that the blue bowl is not directly above the green dot? It's a little bit moved over. What's the deal with that? This is not what I said a second ago. What's the issue? Yeah, is there a guest in the back here? Yeah, what do you think? There's no penalties yet. Absolutely, there's no penalties yet. There will be penalties soon, but right now there's no penalties. Yeah.
The bowl is not necessarily perfectly bowl-shaped. There's like a flattening in one dimension.
Yes. Okay. This is a good point. So I think you're pointing out that the bowl is not circular.
Yes.
I agree with that. So the bowl is not circular. The bowl is elliptical, and this is due to the correlation between the various dimensions. So if the two dimensions are perfectly independent, like if it was about people and it was their height and their weight, and their height did not affect their weight, then you would have a perfectly circular bowl. But of course, in real life, the taller you are, the more you tend to weigh as well. So they will be correlated, and you'll have a longer direction along the way in which they're correlated. In fact, at one point I had this little red line over here. Let's put the red line back. So this line is the line where the sum of x and y is constant, and that is the direction on which the whole thing is stretched. You see it matches this direction. So it's not circular. I would still say it's a bowl. Maybe let's specify. This is a very good point to clarify. It is an elliptical bowl, and very more accurately, it is something called a quadratic form. So the loss function, as a function of beta hat 1, beta hat 2, is a quadratic form. So I did say here that there's a true value, beta 1, beta 2. That's what I drew in green. This was the green dot. Green dot. But the loss function over here, this was the blue bowl, and it doesn't quite match what I saw over here. So why is it the blue bowl is not matching with the green dot? What's up with that? I can turn this back off. So great question. Let me give you guys a minute to think. Try to remember what's going on here. Talk to your neighbors. Let's get some discussion going. What could be going on here? What could the blue dot represent other than the thing that is right above the green dot? What's going on? Okay, I'll let you think for a minute. I'll come around maybe, and then let's have some discussion here and turn our brains on. What's happening? Yeah. Okay, hold on. Green dot is not the optimal game for the bowl. That's a different one, yes. So the blue bowl represents something else, not exactly. Blue one is something, and the green one is something else. And I'm trying to get you guys the difference between them. Yeah, very good. Okay. Okay, so we have a little bit of discussion. Does anyone remember? There were actually two things. There was a green bowl. Let me see if I can find the green bowl. Let's and I guess I'll probably give away too much. What is this? Is this the? Yeah, okay. There is a green bowl, and that green bowl, that one is really right over top of the green dot. And there's a blue bowl, and the blue bowl is over top of the blue dot, and they're two different things. And that's, you can easily get mixed up here. And the way I have written this down on the board so far, I have, I've like nothing I've said is really wrong, but it's kind of misleading because I haven't made a distinction between this green and this blue, and that is really at the heart of what we're trying to understand. So does anyone have a, I guess or remembers what's the difference between the green and the blue here? What's going on? Yes, you have an idea? Yes, that's true. So they have slightly different, they look slightly different. So they're both quadratic forms. So they're both some kind of quadratic equation. And they are two very slightly different quadratic equations. And that's why they're slightly different. Let me give you a hint. I think when I did this one on Wednesday, I was pressing a button. What button was I pressing? I was pressing a button like generate data. Yeah, I was pressing this button, and the blue bowl was jumping around. Why is the blue bowl jumping around? Look, this blue dot. The blue dot really is the minimum of the blue bowl. That is also jumping around. And the blue dot should really be the minimum of the blue bowl, which I think it is. Okay, very good. So we have the green dot and the green bowl and the blue dot and the blue bowl. And here I'm doing some kind of animation here. And the blue bowl is jumping around. What do these things represent? Why is one of them jumping around? Wait a second. What are you talking about? There's something, we're trying to find the minimum of something, but it's jumping around. How could this be? What's going on? Please. Yeah. Yeah, the blue one, so you're saying the blue one is some entire loss function, and then the green one is just like one part of it. Yeah. You're on the right track. The green one and the blue one are very closely related, and they are not exactly the same. And that's because one of them depends on this, the name of this course, the data, n data. So in my little animation over here, I am changing the random seed, and when you change the random seed, I am creating a new data set. And my data set has 10 points, and I'm creating 10 random points, and then I'm using the 10 random points to create the blue bowl. And that blue bowl, it is not the, quote, true loss function or the population loss function. It is the loss function depending on our data set. And I think this is the distinction that you must absolutely have clear in your mind, is there is a difference between the true value and the data that we have. So this is the important distinction that I should put over here. In real life, so there's a true value. There's a true value, that is in green, in the green dot, and that is an elliptical bowl. There is a true loss function, the loss function true, of beta hat 1, beta hat 2. But in real life, you never get to see the true loss function. The true loss function depends on the distribution. You don't get to see it. What you do get to see is the blue loss function that depends on the data loss function. Okay, and we did this all the way back in the first week of the class. The example, the easier example was the 1D example, which was a four-sided dice roll. Four-sided dice roll. Dice roll. And in the four-sided dice roll, the true loss function, the true value of some estimate mu hat is mu hat minus 2.5 squared plus, and the irreducible error was the variance of the dice roll. This was the true loss function, but you don't get to see that. What you actually get to see is the one that depends on data, the data, and we had some mu hat, and it depended on the outcomes, x1 to xn, and it was mu hat minus the average of the x's, x1 plus dot 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 plus xn data divided by n. Let's call this n data, so we remember what it is, squared plus some variance. I won't go into the detail a lot, n data. So the true value is the true average of the dice roll. It was a four-sided dice. The true average is 2.5. The true average is 1 plus 2 plus 3 plus 4 divided by 4, which was 2.5. But in real life, you don't ever get to see the true distribution. You cannot inspect the dice in real life. What you get to see is rolls of the dice. You have this data set, x1 to x2, all the way up to the data. And that is what you get to see. And then your best bet is to do the average of the data that you saw. But of course, these things are slightly different. If the sample size is low, if n data is low, they will be very different. And as the number of data points gets bigger and bigger, they should get closer and closer together. So let's check and make sure that's correct. And let me make sure I don't actually have any alpha turned on. This should be turned off. Okay, there we go. So same story as before. Before, they both had an alpha applied, but now I want to tell the story without the alpha. And now maybe it is more clear. But as I increase the data size, that blue bowl, which is jumping around just by random chance depending on the sample that you drew, the blue bowl should get closer and closer to the green bowl when the sample size gets large. Let's see if that happens. So let's fix some seed, and let's make the sample size go up. And let's make it go all the way up. I think I can change the maximum value to 100, and then I can slowly slide it up. So as you make the sample size bigger and bigger, then the blue bowl and the green bowl get closer and closer together. By the time you have 100 points, they're almost the same. You can go up, you can have 1,000 points in your data set, and then the blue bowl and the green bowl will get closer and closer together. That blue bowl depends on the data. The green one depends only on the distribution, and they're not exactly the same, but they do get closer and closer together. So that is the difference between the true loss function, sometimes called the population loss or the population, this would be the population values versus the sample, right, depending on our data. Okay, so that is the first important distinction to understand. And so let's go back down to a sample size of size 10. And this is like fundamentally the issue is we are optimizing the blue bowl because that's the only thing we can do. And the true value, the green one, is over there. We can't find that. We can just find these blue estimates, this blue dot that is sort of bouncing around the true green dot. Are there any questions or comments about this? Okay, so this is the first thing. And for example, some of the problems that we've noticed is that when things are correlated, let's put back on this red line. If there's a lot of correlation between the data, so right now the correlation is 0.22, but I can bump up the correlation to some huge number like 0.9. If there's a lot of correlation, then the estimate for that we get from the data, blue, is not great. It will kind of slide up and down because you have this long direction of the bowl, right? And you cannot tell where the minimum is of the bowl because you have this long direction where the loss function is almost constant. I could zoom out a little bit to make it look more like, it looks like a pita, I guess. It's like a long bowl shape. But just by random chance, you tend to have the blue bowl, even if it's very close to the green bowl, will have its minimum kind of moved over this way. All right, that's all sort of a recap. Questions, comments, is it making sense? Okay, so then we said, let's try to fix this problem. And we know about overfitting and underfitting. So we said a fix is to add regularization. So in other words, instead of looking at the old loss function, we're going to make a new loss function, the new loss, so that depends on beta hat 1, beta hat 2, is going to be the old loss, beta hat 1, beta hat 2, plus alpha, and then there's a penalty term. And you can put in different types of penalty term. All the penalty terms kind of have this flavor of some kind of norm. I'm going to call it the LP norm of beta hat, where the L2 norm is ridge regression. That is the square root of beta hat. Oh, I guess it's to the power p. Okay, let's put it to the power p. This thing to the power p is beta hat 1 squared plus beta hat 2 squared. That's ridge regression. And if you do the L1 norm, this is p equals 2. And then for p equals 1, you get the lasso, the sum of the absolute values. Okay. So you change the loss function like this. This does all the regularization things that we talked about. It decreases the variance. And another thing that it does that we can see in our picture. Oh no, my mouse is complaining. Okay. Okay, we're back. Let's do that. Let's turn that on and see what happens. So that's what's called alpha over here, is the strength of this regularization term. And the blue bowl is actually what you get for ridge regression, so adding on the squares. And if I minimize that, you will see that it is sort of shrinking in towards 0. So the blue and the green over here. Notice actually there's a little mislabeling here. The green bowl is now the true ridge regression value, which is different than the true value, right? So the green dot and the minimum of the green bowl are now slightly different. But the value that you get moved in closer to 0. The bowl got more round, and so it is less subject to these random errors. It's a little bit more robust because it's a rounder bowl, and it's more likely to have the minimum near where we want it. There we go. Okay, that was ridge regression. If we add on, let me pause this this data making process. If I can find the button, generate data. Let's pause this. So we were adding on this this sort of square term, this like really circular bowl, and that pushed the whole bowl towards the middle. It made it more circular. That was very good. But you can also do the so-called lasso regression, where instead of doing x squared plus y squared, you do this. You add on a, let's turn these off. You add on a little pyramid, this like diamond-shaped function. And this comes from the fact that the set of points where the absolute value of x plus the absolute value of y is a constant is this diamond shape. So we're adding on this to it. And when you do that, so let's get this blue bowl out of here, and let's move towards the purple bowl, which is the lasso. Same kind of thing with the lasso. And that is this situation over here. And you'll notice, okay, let me see if I can get the green one out of our hair for a moment, so we can see clearly the purple bowl. Where's the data? Green, ridge regression. There's my green bowl. Okay, so there's the purple bowl. And the thing to notice is that because we have taken the original bowl and we have added on this like pyramid, you end up, you can see it kind of right there. Maybe you can't see it very well, but there are little kinks in the surface. So the little squares that we added on, they appear in this surface. They have this little, right on the edge here, is a little kink in the surface. It's no longer perfectly smooth. It has a sort of a corner going on here. And if I increase the strength of the regularization, I up that alpha value, you'll see more and more corners. So let's make it very cornery. There's a alpha equals 5, and you can see that on the back there, you see that corner happening. And those corners, because we have changed the loss surface by adding in the corners, this is a useful feature because it tends to find minimums that are zeroing out some of the coordinates. So because it has these corners, the minimum happens to be on these corners, and that is exactly above the axes. Okay, so let me turn on the minimum, the lasso minimum, which is here. Did I get it? Yeah, so that's the purple dot. And as we change the data over and over again, the value will move around. Here I have set the regularization to such a huge extent that it's always near 0. That's not great. Let's maybe bump down that alpha value a little bit. Okay, let's. So there's still corners, but not so extreme. So look at that. Sometimes it reduces, it eliminates one of the variables, and sometimes it does not. So a lot of the time, the minimum, depending on the data, sometimes the minimum is over here, and one variable is set to 0. Sometimes the minimum is down here, and the other variable is set to 0. And sometimes the minimum is somewhere close to where it was originally. It just depends on the strength of the regularization, the alpha, how much you added, and also the random data that you got. Okay, so this, some of what I said is maybe a recap, and some of what I said is maybe new. Are you guys on board so far? Any questions? All right, so what we're gonna try to understand now is we're gonna try to answer a question of the form, what has to happen for it to be eliminated, and what has to happen for it to not be eliminated? So when does it do one thing, and when does it do the other thing? Okay, so we're gonna try to make a question like that, and you are going to answer it. So if you understand what's going on, it'll be a nice, easy question. If you don't understand what's going on, it will reveal what you don't understand. Okay, so here is the question we want to get to. Question. When does the lasso eliminate variables? So in what situations will that corner on the loss surface be enough that the minimum is really on the side, and in what situations is it not enough? Okay, and we're gonna learn one more fact that's gonna help us with this, fact. And the fact has to do with what I call the dual view of optimization, the dual view of optimization, minimization. Optimization, okay, there we go. And the dual view of optimization says there are two different ways of looking at regularization. So the first way we've talked about a few times, which is to think of it as a function of alpha. So as a function of the strength alpha. As a function of the strength alpha. And this really is what we've been doing. So we've been saying we have the loss, and the loss depends on beta hat 1, beta hat 2, and alpha. And it really is the old loss, the original loss of beta hat 1, beta hat 2, plus alpha times this regularization term. And let me use, let's do the ridge regression for now, beta hat 2 squared. So it depends on alpha through this multiplication term. And as you increase alpha, you make the coefficient smaller and smaller. You increase this penalty term, and then eventually the only way to minimize this whole thing is to make beta hat 1, beta hat 2 very close to 0. And this is the kind of thing we saw last week as well. So this led us to plots that look like this, where we have, let me do a plot like this one. Yeah, okay, this is the plot of the baseball hitters that we did last week. And on the x-axis, we have the ridge regularization parameter, that alpha value. And as alpha increases, all the beta values shrink in towards 0. All right. Another way you can view this is this kind of plot. So here it is in the situation, back in the two-dimensional situation, we have beta 1 and beta 2 on the x and the y axis. And I am plotting the color tells you the size of the alpha. So it starts over here when alpha is really small. The true value was 2, 3. And then as you shrink this, it is shrinking in towards 0. So it starts here and it goes all the way down to 0. Eventually, if the strength is really, really big, then the value you get is 0. Are there any questions or comments about this plot or what is being shown here? So we're showing the beta value shrinking in towards 0. Okay, here is the dual view. So that's the regular view. Now that we have that loaded into our RAM, the other way to do it, too, is as a function of the norm, beta hat 1 squared plus beta hat 2 squared. And I'm going to call this equals C. And so here is the observation. Yeah, let's call that C. Okay. So as a function of the norm, when you are doing this, here is a totally other way you could make the same exact picture. You'll notice this graph, which starts at 2, 3, and it shrinks its way in. It sort of intersects every possible circle, every possible radius, exactly once. And that's because as you're minimizing, you're finding the minimum of this function. You might as well minimize it on a circle. And that is the dual view that I will write out right now. So the dual view says, instead of treating the loss as a function of alpha, let's treat it as a function of C. So the loss of beta hat 1, beta hat 2 as a function of C is equal to the old loss, beta hat 1, beta hat 2, plus alpha times C, because this value is C, and this is on the set beta hat 1 squared plus beta hat 2 squared equals C. In other words, a circle. A circle. So in other words, I could have drawn this picture by saying, where on the circle of radius 2 is the loss function minimized? Let's find that point. Where on the circle of radius 1.5 is the loss function minimized? Let's find that point. And by connecting all these dots, I would have gotten the exact same curve over here. So the dual view of optimization says that instead of treating the alpha as the parameter, you can treat the value of beta hat 1 squared plus beta hat 2 squared as the parameter, and it's totally equivalent. So the curve we get from the curve, let's say as alpha changes, the curve we get from picture 1 is the same as for picture 2. We get from picture 1 is the same as for picture 2. So in other words, instead of thinking of alpha getting stronger and stronger, and that causes the beta hats to get closer and closer to 0, you can explicitly think of the value of the size of the coefficients and then vary that, and then that will shrink towards 0. Okay, so there you go. Oh, I suppose, okay, I wanted to erase this. Alpha times this value. Okay, let's leave the alpha there. I think that's less confusing. Here is a good example. In this plot, I believe we have at some point, okay, this is the RMSE, trying different ridge parameters, choosing the best parameter, and the lasso. Okay, the same kind of thing works with the lasso. Do I have one with the coefficient? Okay, these are the coefficients, and then this is the error. Okay, I think the one I'm looking for, yes, okay, I'm looking for this thing. And what am I looking for? The error, okay, these are the bowls that we had before. What am I looking for? The error functions. Do I have one with the coefficients? Okay, yeah, this is great. So these are the coefficients shrinking down to 0, and then do I have the norm? Okay, well, this is good enough. So the point is that the sum of the squares of beta 1 and beta 2 can reparameterize the ridge parameter. So instead of thinking of alpha getting large, you can think of betas shrinking down to 0, and it's exactly the same thing. They're totally equivalent. Okay, why am I mentioning all this? It's going to be to answer the setup. We're going to use this dual view to answer a question in Mathematize, and that is here. So that's the first Mathematize question. Here it is. Okay. Where does the lasso eliminate variables? So here's the setup. We're going to consider a purely circular mean squared error loss function. So the bowl is perfectly circular, and it is has some minimum, beta star 1 and beta star 2. So that's the ordinary point. And I've drawn a little picture of this thing over here. So there's some bowl. You can think of this as the top view. And these are the contours of the bowl. So this is like a bowl coming out of here, coming out of the screen. And these circular contours are the level lines of the bowl, the loss function. And the center of the bowl is beta 1 star, beta 2 star. That is the true minimum that we are trying to find. Okay. And as you make the radius bigger and bigger, the bowl gets taller and taller, right? So these are like low values of the bowl. These are big values of the bowl. You have to picture the bowl coming out of the screen and getting large. That's the loss function that we're trying to consider here. Okay, let's read the rest of the question. You apply the lasso and are optimizing under the constraint that the absolute value of beta 1 plus absolute value of beta 2 equals 1. In other words, you're trying to find the minimum value of this bowl, but only on this diamond shape over here. So this diamond shape, those are the only points we're looking at. And by doing so, it's a dual view of setting the value of the regularization. Instead of setting the value of the regularization, we're saying we're going to only look for solutions that are somewhere on this diamond. Okay. All right. Here's the statement. Depending on where the minimum lies, the ordinary minimum, beta 1 star, beta 2 stars, the lasso will sometimes eliminate a variable, and sometimes it will have both variables as non-zero. So sometimes it eliminates a variable, sometimes it doesn't. In which regions, beta star 1, beta star 2, does the lasso eliminate the variable? So the statement is, whether or not it eliminates variables depends on the location of beta 1 star, beta star 2, and I want you to select the regions where it works. And the regions are labeled by the region of a clock. There's 8 possible regions. There's 12, 130, 3, 430, 6, 730, 9, and 1030. And I want you to think of where would this thing have to be for the elimination to work. If it's here, will it eliminate a variable? Yes or no? If it's here, will it eliminate a variable? Yes or no? If it's here, will it eliminate a variable? And you know what's going on now. You know this is the bowl. You know we're trying to minimize the bowl. You know that we're trying to look on this little diamond. And if you put together all the pieces, you should be able to answer this question: where are the variables eliminated? Okay, I'm going to set you loose on this. Does anyone have any questions or comments about what's going on? Is the question clear? The question's not clear. Someone shook their head. Is that right? The question's not clear? Okay, let's see. Let's see which part of the question is either clear or not clear. So we have a bowl. That was the first thing. Let's go to this plot. Is the fact that this big red target is a bowl, is that clear or not? Put your hand up if you understand that this red thing is supposed to represent a bowl. You know, if you're in a different class and someone draws this on the board and says, this is a bowl, they will go, you're crazy, man. That's not a bowl. But in this class, I hope I have explained enough that this is a bowl. Okay, so put your hand up again. Is it clear that this is a bowl? Okay, that is a bowl. We want to minimize the height of the bowl is the thing we're minimizing. So you imagine the bowl, and you are trying to find where on the bowl is the height the lowest. Of course, the answer to the question, where is the height the lowest, is exactly on the bullseye, right? But we're not trying to find the minimum anywhere. We're trying to find where on the bowl is it minimum that is on the purple diamond. Where on the purple diamond is the minimum of the bowl? And let's put it here. Where on the purple diamond is the minimum of this bowl? Is it over here? Down here? No, the bowl would be really, really big over here. Where is the height of the bowl the minimum? Oh, I think it's this one, right? And you can see that if you make this bigger and bigger, the bowl is first intersecting this point over here. So its height everywhere here will be constant, and that'll be lower height than anywhere else. So this is the kind of imagining you have to do. You have to imagine this as a bowl, and you have to imagine what would it mean to find the minimum of the bowl on this diamond. Okay? That's what we have to do. Does that make any sense? Finding the minimum of the bowl. Last but not least, you have to ask yourself, okay, the minimum was here. So that's the value. Our lasso will return this point. Is that eliminating a variable or not? Is that eliminating a variable or not? Okay? And that is the answer for one of these regions up here. Now you have to redo the whole kind of thought. What happens if it's in this region? What happens if the minimum was over here? In this region, what's the answer? Are we eliminating a variable, yes or no? In this region, are we eliminating a variable, yes or no? In this region, and so on. Fortunately, there is a pattern. So once you see the pattern, and I'll let you think about it, you should be able to answer this question: when does the lasso eliminate a variable? Which is what I want to get to. Okay, hopefully that helps. Let me give you some extra time here to do this with the clock, and then we'll go from there. Oh yeah, and there should be a link here if you want to play with the thing. You can type in this code, or you can, if you copy paste it from F25, that should take you to this little Desmos thing, and you can play with it yourself. I find it's helpful to imagine the bowl by sliding this up and up, right? If you slide this, that's going up the bowl, and then by going up the bowl, you can find where its minimum is more easily, or you can just imagine it in your head. Okay. Okay, there's like 1 minute left. If you have no idea, try to focus on just the answer to 12. Does 12 eliminate a variable or not? Try to get just that one. And don't worry about the rest if you're totally confused. If you know what's going on, then maybe you see the answer right away. Okay, let's see what people thought for 12 specifically, and then we will look at the other ones shortly after that. So where are we eliminating variables? Did we eliminate a variable at 12 or not? Okay, let's see. Okay, so out of 18 people who answered, it seems like the pattern is 12 or 13 people are saying 12, 3, 6, and 9. If you're in the region 12, are you eliminating a variable, yes or no? Let's examine that one in detail. And so again, if you start up here, the question is, where does the minimum happen? And as we said before, the minimum happens at the first time the bowl touches the purple thing. So as you go up the bowl, so this is moving up, 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 and then bonk, at this point, you perfectly touch this little green, or this purple diamond. And so the minimum, it will happen exactly here. And so what this is saying is, in this situation, with the amount of regularization you added, the minimum of the diamond, of this like pyramid plus the bowl will happen exactly here. The minimum is here. And in that situation, are we eliminating a variable? Yes, we are. This is a nice corner. And so the x value here is 0. The y value is 1. And so we have eliminated the variable x. X is exactly 0. So that is the correct answer to 12. So if you selected 12, you got it right. Now the question is, what about at 130? Only one person said we're eliminating a variable at 130. But of course, we've seen many times where the crowd is wrong. Let's see what happens if you're in the 130 region. So once again, the true value we want is somewhere in the region, maybe over here. Where is the minimum? The minimum on the purple diamond is going up, 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 up the bowl. The minimum is here. And in this case, the minimum will be on the side of the diamond, right there. So are we eliminating a variable in this case? The answer is no. The beta 1 value is non-zero. The beta 2 value is non-zero. We are not eliminating a variable. And so the correct answer is indeed to not select 130. And following the pattern, 3 o'clock is going to be symmetric with 12 o'clock. If you're in the 3 o'clock region, then it also will work. Right? The minimum happens at the corner. Because the corners are corners, the minimum happens at the corner, and you eliminate a variable because that is right on the axis. So you guys got it right. Most people got it right. Let's reveal the correct answers. So very nicely done if you figured out this pattern. You'll notice that this is for the lasso, you eliminate variables. For a range regression, this would be a circle, and you would almost never eliminate a variable. For a circle, the minimum would happen just somewhere random on the circle, and you would not be eliminating a variable. Because the lasso has these corners, that is the secret sauce of why it eliminates variables. So maybe we can write this down now. The lasso eliminates variables whenever the minimum happens at a corner, and this happens for most of the plane. Most of the plane is like this if the regularization strength alpha is big enough. Big enough. Okay, and that's because, if you making alpha big means making the little diamond, let's make it a purple diamond like we had before. Alpha big is purple diamond, C is small. And when C is small, most of the plane lives in these regions, right? Most of the plane is here. So most random numbers in the plane, except for these narrow strips, are somewhere in this region. C is small. Most of the plane is here. Okay, and that's the theoretical reason why people like the lasso. In practice, people like it because it eliminates variables. Then you don't have to collect the variables it eliminates. It makes things more interpretable. You can say, my estimate only depends on these 5 variables instead of saying my estimate depends on these 100 variables. So eliminating variables is good. And in higher dimensions, you have to think in more than 2 dimensions, but the same story holds. Okay, that's the story of why the lasso eliminates variables. I think they have a picture like this in the textbook as well, but now we have done it to death in the class, so you can see why. Are there any questions or comments about the lasso or anything we've done here with these loss surfaces or anything like that? Okay, so we're going to move on to another topic, which is dimension reduction. Dimension reduction. And this is a very linear algebra focused thing, linear algebra flavored. Topic to start with. And so the idea is this: we have a bunch of points. Let's to start with, our first example is going to be in 2 dimensions. We have x1 and x2 data points that have 2-dimensional, so 2-dimensional data. And the question we're going to ask is, how can we represent the data in 1 dimension the best way? Or let's say, what is the best way to represent the data in 1 dimension only? What is the best way to represent the data in 1D only? Okay, and what does this even mean? So if it's 2-dimensional data, how could you represent it in terms of 1-dimensional data? So what we want to do is we want to take our data set, which has an x1 and an x2 value for every data point, and we would like to turn it into, so before we had x1, 1, x2, 1, the first data point, then we have the second data point, and so on, all the way up to the number of data points, x2 number of data. And we would like to crunch this all into 1-dimensional data. What is 1-dimensional data? Well, it would just be one number for each one. What should we call this number? Let's call it D. So we're going to have a D1, a D2, a D, and data. So every single data point, which was 2-dimensional, was 2 numbers, x1, x2, it got turned into 1 number. And we would like to do it in such a way that when we convert it back, we're going to convert it back. Of course, converting it back cannot be perfect because this is 1-dimensional data and this is 2-dimensional data, but we would like this to be as good as possible. As good as possible. Okay. And how are we going to do this conversion? The conversion formula is going to be that x1 is equal to something times the d, something times d, and x2 is something times d. So in other words, we're going to take the value and we're going to multiply them in the sort of only possible linear way to get back the x's. And we're going to call these coefficients, let's call them alpha and beta. So don't get confused, this alpha is different than the alpha before, it's just the letter alpha. As vectors, you could say the vector x1, x2 is equal to the vector alpha beta times the vector d. So in other words, we're trying to reconstruct a two-dimensional vector from a one-dimensional vector by using some fixed vector to do it. This is the game, and we want it to be as good as possible. We have to figure out what does as good as possible mean, and then we have to figure out how on earth we're going to solve for this alpha and beta that makes it as good as possible. But is the setup clear so far? We have two-dimensional data. We want to crunch the two-dimensional data down into one-dimensional data so that when we uncrunch it, we keep as much of the data as we can. All right. Let's do it with a picture. This is the algebra. Let's do it with a picture. You know I love a good picture. Okay, here we go. Here is the picture. Same kind of thing. Let's turn everything off. Okay, here is the data points. Let me put this in projection mode. So the data points, the x1, x2, I have drawn them over here as little green dots. So here's x11, x21, right? 5 and a bit by 6 and a bit, and so on. So these are 10 data points that I would like to compress down. And I even have one point over here that I can move around. So this point can be anywhere I want it to be so that we can see what it's doing. So that's the original data. And then our job is to compress this down into a single number. So each of these will get compressed down into a number, and then we will reconstruct it by doing this multiplication by alpha beta. Okay, here's a good linear algebra question for you. x1, x2 equals alpha beta times d. What do these d, if we make x's, x1 and x2 this way, what shape will these be? In other words, what is the set? What does the set of all possible x1 and x2s such that x1, x2 equals alpha beta times d, and d is any number, d is some number, look like? And so I'm going to fix an alpha beta. For some fixed alpha and beta, what does this set look like? This is a classic linear algebra problem. When I taught linear algebra for first-year students, this was always a question on the midterm. What does this look like? This is a great question. Let me make a mathematize with this. I will let you think for a few minutes. So you fix alpha and beta. What does it look like? The more specific you can be, the better. But you should know at least a little bit what it looks like. Let me make a, this is a great one. Okay, it is live on Mathematize. What does this set of x1, x2s look like? Describe what this thing is. So we're letting the d value change. It can be all possible d values, and we're reconstructing x1, x2 using this alpha and beta, and we're saying, what is it going to look like? What are we going to get at the end of the day by doing this? That is the question you need to answer. And you should hearken back to your linear algebra days. Okay, let me give you a few minutes to think. I'll come around and I will see what people are doing. Let me see. I'm going to look at your pages and see if you have pictures that are drawn that look good. What are you guys doing over here? All right. Nobody has a picture. Why don't you make alpha and beta if it's too abstract for you, let's check, plug in your favorite value of alpha and beta. What's your favorite number? Let's say alpha equals 3 and beta equals 2. So we're looking at x1 equals 3D and x2 equals 2D. What does that look like? What kind of shape would that be? Maybe that's a little easier to intuit. Okay, it's live on Mathematize. In a minute and a half, I will take your answers. Your answer could potentially be, I have no idea. But this, this is the kind of thing that goes back to your high school days. I'd say in high school you did it with 3D and 2D, and then in university you did it with alpha and beta. But either way, the shape should be something you've seen before. Okay, put in your guesses, and let's see if people were able to recall this shape. Okay, what did people say? Haha. All right, lots of different things. Sigmoid, cube, slope. The biggest one of all is the word line. Let's see, did a lot of people say a line? Straight line, very nice. A line with slope beta over alpha. This is a beautiful, beautiful answer. Looks like a straight line. It's not a plane, it's the line. So, okay, 3, 4, 5. Yes, okay, this person wrote the same thing as this person. I would guess they are in cahoots. This is too similar. They did it together, okay. Oh, another person. All right, maybe those three in the back. All right, but that's right, that's correct. So, where did it go? Here it is. So this is what we're doing. We're doing a line. Here it's called AB. I was calling it alpha beta. That's because I don't have an alpha beta key on my keyboard, but I have an AB. And I can change the direction of this line by dragging it around. So here is the direction A equals 5, B equals 5. And that is this nice blue line over here. And what I'm saying is I want to take the data and I'm going to compress it so that the data always lies on the blue line that I have chosen. You'll see that this little green dot, it got sent down. It was here and it got moved down to here. These ones, they both got, even though they're two different green points to begin with, when I moved them onto the blue line, they got pushed very close together. So even though they're far apart in real life, when I put them on the blue line, they're very close together. You can do it for any data, and this is called the projected data, the projection, and no matter where you put it, you sort of take the right angle to the line and you eliminate that component. So this is the basic lesson you learn in linear algebra class, is that for any data point, any green dot, you can write it as a sum of two vectors, some direction times the blue vector plus some direction times the green vector. And if you delete the component in the green direction, you will project the data from wherever it was to somewhere on the blue line. So this is called projection. Let's write this down. So the operation of x1, x2 gets sent to alpha beta times d is a projection onto the line. Let's call this line L, lowercase l. And L is the set of all possible alpha beta times d's, where d is a real number. That is the line we were just talking about in the question. Amazing. Okay, so in other words, the line, we start with a point, we project it onto this line, and the value of d is some formula. The formula for d, so given alpha beta, the formula for d is what should we say? Well, first of all, does anyone think who has seen projections in their undergraduate class? Has heard of projections? Who has never heard of a projection before? Who maybe you've sort of heard of it, but you're scared to put your hand up? Okay, most people. All right, so you probably don't remember this stuff, projections. The formula for projections, let's say it's given in terms of inner products, given in terms of inner products / dot products. Okay, so same kind of question. Who has heard of an inner product or dot product before? You had a class where they said the words inner product or dot product at some point in the class. Who has never heard of an inner product or dot product? Who's like, maybe, I'm not really sure. Okay, lots of people. Who put your hand up if you're scared to put your hand up? Nobody, what a surprise. Okay. All right, so inner product / dot product. You might remember they are this kind of notation. So the you have some vector v and some vector w, and this is some number equals a number. Okay, and I believe the formula for d is d is going to be something like the inner product of the vector alpha beta with the vector x1, x2, maybe divided by the norm of alpha beta squared. So this is the formula. This is the projection formula. If you look up the projection formula, get over here. And it says to figure out how far over you should go, you take the inner product of x1 and x2 with alpha times beta. Okay, that's very nice. Okay, you don't necessarily need to know the formula, but you do need to know the idea that we're taking the original data and we're smooshing it onto the line. Okay. Now is the question. Oh, I can show the formula over here. Okay, yeah. Oh, let me write down what this formula is. Okay, this is nice. Let's do a little bit of expanding because this is nice. So d is this much. The inner product between alpha beta and x1, x2 has a nice formula. You multiply the x coordinates together, you multiply the y coordinates together, and you add them together. So this is alpha x plus x1 plus beta x2. And then I suppose there shouldn't be a square on the bottom. On the bottom, you have the norm, which is the square root of the components, alpha squared plus beta squared. So this is the amount you need to move for a given point x1, x2. This is the amount we're going to move in the direction alpha beta. And therefore, the actual point is some nice formula, which is listed over here. Okay. So here's the formula. And it's got this a times c over b plus b times d. This is the kind of thing we're doing. These are projecting the points. These are the formulas. So if you're into this stuff, you should check it out and see what these points are. Okay. Now is the question we're actually interested in. Some basic linear algebra review, which is, what direction is the best? Is it better to do this way and project all the data down onto this line where the x value and the y value are the same? Or is it better to go like this way and where they're kind of like negative of each other? There's some special directions. If you did something purely this way, that would say delete the y coordinate. You see, by projecting down this way, we're deleting the y coordinate, and our vector is only keeping the x coordinate. And the question is, what should we do? How should we choose which way is the best? What way should we do it? Okay, and so that's what we're going to look at. And I have a mathematized question for you, sort of like to think about at a high level here. What are we trying to do? And the question says, when you're reducing from 2 dimensions to 1 dimension, to pick the best direction, we should either make the projection of the points as spread out as possible, or make the projection of the points as close together as possible. Which one do we want to do? What makes more sense intuitively? Okay, and I have the picture again for you. And look, I can cycle through some of these values to make it move around all wonky. And you tell me, when does it look the best? When is the projection the most useful? When is it sort of doing what we want it to do? Okay, I'll let you think for a few minutes while that zooms around. What direction is the best? Okay, and it's multiple choice. Either we want them to be spread out or we want them to be close together. All right, 10 seconds left to choose your choice. Okay. Mathematize this one? Okay. What's better? All right. On a score of 12 to 5, people want to make them as spread out as possible. So let's look at the 2 possibilities, either spread out or not, and see which one is better. Where'd it go? Desmos. Okay. So let's stop the animation. So basically the options are, you can spread them out. Spread them out would be something like this. You see they're all spread out. Or push them together would be something like this, where they're all smooshed together. And I think the best way to phrase it is, this situation is quite bad. You see, all the data, before it was nicely spread out, like we could tell them all apart. And now they have all been compressed into this thing. They all look the same. So by doing it in this direction, where they're all close together, we're sort of losing a lot of information. Whereas if we do it this way, we're not losing that much information. We can sort of tell which one is the most extreme. It's that one. We lose a little bit of information about these two. We kind of can't know which side of the line it was on anymore. But they're pretty close to the line, so we're not losing too much. So the answer is we want to make them as spread out as possible, as many people figured out. So well done. And now here's the mathematical question. How can we measure how spread out things are? How can we measure mathematically? So okay, we want to make them spread out. Let's start with that. We want to make them spread out. How can we measure mathematically how spread out they are? So what operation could you do with these values that we have over here in our nice picture to measure how spread out they are? And this is a topic we've done many times before. How can you measure how spread out things are? This is another good one for mathematized. Let me make yet another mathematized question. How can we measure how spread out the points are? Okay, and once again, I will let you think, because that is the heart of math, is thinking, not being told. Okay. And I'll give you a hint. It's something I think we've used this almost every day since the beginning of the term. The answer to this question is something that appears a lot in the course. Okay. Okay, 10 seconds left for you to tell me how to measure. I have a bunch of points. How can I measure how spread out they are? What would you do to all the points to measure how spread out they are? Okay. Let's see what people said now. Ha! The variance. That's perfect. The variance are the sum of the squares. Those are two different ways of saying the same thing. The standard deviation is the square root of the variance. Of course, if you measure one or you measure the other, it's the same kind of thing. So very nice. So the variance, it's not the distance, it's the sum of the squares. So it's kind of, it's not just the distance. That's an important thing. It's how much the distance varies, the variance. Okay, that's very nice. So the sum of the squares or the variance is the answer to this question. Answer, use the variance of the distances, also known as the sum of the squares of the distances, And this is the one point in the course, up until now, we've always been talking about minimizing the variance. Make the variability as small as possible. Make the errors as small as you can. But this is the one time in the course we want to spread them out. So we want to maximize the variance. We want to make this as big as possible to spread the points out. So this is a funny twist of fate. We're going to maximize the sum of squares, not minimize the sum of squares like we normally do, right? Because we're trying to achieve a different goal. In previous parts of the course, we were trying to estimate things as accurately as we could. In this case, we're trying to spread things out as much as possible to find the direction that is the best. And we can put that on our little chart over here. So we can turn this on the plot. I really should combine these. Let's combine these so I stop having to go back and forth. Okay, I have a little label here for the sum of the squares. Oh, these are the dot products. These are the d values on the axis that I was talking about before. And we want to do the sum of the squares, which I call the score, the sum of the squares. And there it is in orange. The sum of the squares for this direction is the sum of the squares of all these differences. It's 4.6. If I change the direction, you will see this go up and down. So if I go and I change this, that value will go up and down and up and down, and up and down and up and down. We want to find out where it's maximum. I'll tell you where it's minimum, where all the points are all together. They have a very, very small variance. All the points are really close together. The variance is only 0.7. All the points are projected near 0. They're very close together. On the other hand, if you kind of go up, 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 it's getting bigger and bigger. Here it's 3.6. That's pretty good. Can we do even better? And we can keep going, 4.3, 4.5, 5.7, 5.9, 4.6, 4.63, 4.65. Oh, it's starting to go down again. So I've kind of reached the maximum, and I'm starting to shrink again. So that's too small, that's too small. The maximum is somewhere in between, at where the sum of the squares is 4.65 in this direction, because it has the maximum of the sum of the squares over all the directions, is the direction that spreads the points out as much as possible, and that is what we are looking for. So this is the direction. Okay, so mathematically, we want to find alpha beta so that we are maximizing over all possible alpha and betas the variance of what I called in the very first slide the DIs. The DIs. The DIs were the projections, how far over you were. And we were maximizing the variance of the DIs, or the sum of the squares of the DIs. And this is the maximum over all alpha and beta. Remember, the DI formula had some formula like this. So alpha x1i plus beta x2i. And that is the coordinate. And then we square it, and we sum over all I. I equals 1 to the number of data points. And we're dividing by alpha squared plus beta squared on the bottom. So we're trying to make the points as far as possible. This is a very linear algebra thing. And this is what is called the first principal direction. The first principal direction of the data. It is the direction in which the direction that maximizes how spread out the points are. That maximizes how far out, how spread out the projections are. Okay. And by doing that, it turns out this has also minimum reconstruction error. It turns out, also has the minimum reconstruction error. And what do I mean by that? I mean, if you go to the picture that we made, not only are the points as spread out as possible, but if you were to add on the sort of errors that we made, so you take the blue dot and you have to add on a little bit to get back to where they were, that will be minimized. The reason that is because the sum of the variances in the blue plus the sum of the variances in the green, they have to add up to the sum of the variances of the original data set. So by maximizing one of them, we have minimized the other one. That is the first principal direction. We have found this line. This is the story of taking two-dimensional data and turning it into one-dimensional data, and we've done that more or less completely. Now, of course, in real life, you don't have two-dimensional data. You have n-dimensional data. So the extension, which is to take n-dimensional data for some lowercase n, and we're going to convert it into some lower dimensional, m-dimensional data, where m is some smaller number. N is bigger than m. We're shrinking the size of the dimension. We've done the example with 2 to 1 in a lot of detail, and we've done the first principal direction. You will see that there is a second principal direction, a third principal direction, and so on, and it will operate by the same principle. So in other words, doing 2 to 1 has all the hard mathiness of doing n to m, and that's what we'll work on next time. This is a good place to stop if there's any questions or comments. Any questions or comments here so far? The 2 to 1 is clear. The next class, I will assume you know everything about the 2 to 1, and then I will do n to m. Here is a warm-up question that we will cover in next class as a sort of example of this kind of thing, which is what I call exercise 3. And this has multi-dimensional data. How big is my dimension? My n dimensions are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I have 17 dimensional data. N equals 17. I have 4 data points. These 4 data points are actually 4 countries. So each of these is a country. And they're kind of related. This is how many of these different types of foods the countries import. Of the 4 countries, one of them is the odd country out, and is sort of different than the other 3. And if you stare at this for long enough, you stare at the 17-dimensional data for long enough, you can eventually puzzle together which one is the odd one out. Of course, it would be so nice if we could take the 17-dimensional data and we could turn it into 1-dimensional data or 2-dimensional data. Then it would be a lot easier to figure out which one's the odd one out. Some people have figured out which one's the odd one out already. I'm very curious. Some people already know. Ha! 4 people, I think, took random guesses. All right. Shame on you for taking a random guess before thinking about it. Let me reopen it again. So let's. So we've caught those people. Now let's reopen it again for everybody else. Repeat exercise. So please now think about it before you answer. Don't just answer randomly. Which one is the odd one out? And on Monday's class, we will take this data set, which is 17-dimensional, and we will compress it down to 1 or 2 dimensions. And when you compress it down to 1 or 2 dimensions, which one is the odd one out will be very easy to see. So this will be an application of what we're doing. For now, I want you to do it the hard way, to stare at the 17-dimensional data and see if you can figure out which one's the odd one out. I'll be honest with you, this one, I really struggle with it, but in previous years I've done this, the students are always able to get it. So if you stare at this for long enough, you eventually can find the one that's the odd one out. But I find it quite tricky personally. But okay, I'll let you do it. You can think until the end of the class, which is in 4 minutes. Wow, that's a lot of time. And then we will take it up on Monday. Don't forget your draft is due on Friday. I will open it up on the pair tool, and I'll have somewhere where you can say who your partner is. And that's for the cooperators data set. Yes. Any questions or comments about that? It'll be the same kind of thing as project 1. Okay, so take your time, stare at this, and then after you answer, I'll see everyone on Monday.